And this is Sirichandra from CSC F section, roll number 24951A05BN. Today I am going to talk about soil corrosion. Introduction to soil corrosion. Soil corrosion refers to the deterioration of materials, primarily metals, due to electrochemical reactions in the soil. This process can significantly impact infrastructure, including pipelines, foundations, and underground utilities. Understanding soil corrosion is essential for effective management and prevention strategies. Causes of soil corrosion. Soil corrosion is driven by various environmental factors including moisture, temperature, and pH levels. The presence of soil, salts, organic matter, and microbial activity can accelerate corrosion processes. Different soil types exhibit varying corrosivity, influencing the choice of materials in the construction. Let us learn more about factors influencing soil corrosion. First is soil resistivity. Lower resistivity often leads to higher corrosion rates. Resistivity is influenced by moisture content, salt concentration, and temperature. Next is moisture content. So water in soil acts as an electrolyte promoting corrosion. Dry soils generally have lower corrosion rates compared to wet or water saturated soils. pH levels. In acidic soils tend to accelerate corrosion, especially for metals like steel and iron. Neutral or slightly alkaline soils are less corrosive. Chloride and sulfate ions. High concentrations of chloride and sulfate ions in the soil can increase corrosion, particularly for metals like steel and aluminum. Next is oxygen availability. Aerated soils can promote localized corrosion such as pitting due to differential aeration. Soil type and texture. Clay, slate, and loamy soils can retain more water, which may lead to higher corrosion potential. Sandy soils generally drain better and may have lower corrosion risk. Microbial activity. Certain bacteria, such as sulfate reducing bacteria, can accelerate corrosion through their metabolic activities, such as microbiologically influenced corrosion. Next is temperature. Higher temperature can increase the rate of electrochemical reactions, potentially accelerating corrosion. Next is types of soil corrosion. There are several types of soil corrosion, including uniform corrosion, localized corrosion, and galvanic corrosion. Uniform corrosion occurs evenly over a surface, while localized corrosion can lead to pitting or serious corrosion. Galvanic corrosion happens when two dissimilar metals are in contact in an electrolytic environment. Environmental factors affecting soil corrosion. Soil moisture content is a critical factor that influences the rate of soil corrosion. Next, temperature fluctuations can affect chemical reactions that contribute to corrosion processes. Soil pH plays a significant role in determining aggressiveness of the corrosion environment. Soil resistivity and corrosion. Soil resistivity is a key parameter that indicates how easily electric current can flow through the soil. Low resistivity soils are typically more corrosive, leading to increasing rates of metal deterioration. Measurement of soil resistivity can help predict and mitigate corrosive risk for buried structures. Biological factors in soil corrosion. Microbial activity in soil can lead to biocorrosion, where bacteria produce corrosive byproducts. Sulfate reducing bacteria are particularly notorious for causing localized corrosion. Understanding microbial influence is essential for developing effective corrosion prevention strategies. Corrosion prevention strategies. Coatings and wrappings. Apply protective coatings such as bituminous or epoxy based coatings to create a barrier between the metal and the soil. Next is cathodic protection. Use sacrificial anodes or impressed current systems to protect metals from corrosion. Next is soil treatment. Alter soil conditions by neutralizing acidic soils, improving drainage, or reducing chloride content. Next is material selection. Use corrosion resistant materials such as stainless steel, ductile iron with protective linings of plastics. Regular monitoring. Conduct inspections, soil resistivity testing, and potential measurements to assess and monitor corrosion risk. Cathodic protection is widely used method to mitigate corrosion in buried pipelines and tanks. Coatings and Coatings and linings can provide physical barrier between metals and corrosive soil. Regular inspection and maintenance is crucial for identifying and addressing corrosion issues early. Impact on infrastructure. Soil corrosion poses significant risk to infrastructure, leading to costly repairs and replacements. Corroded pipelines can result in leaks, environmental contamination, and safety hazards. The integrity of foundations can be compromised, leading to structural failures. Next is testing methods for soil corrosion. Various testing methods such as electrochemical impedance spectroscopy can assess corrosion rates. Soil sampling and laboratory analysis can determine corrosivity levels and contributing factors. Regular monitoring of buried structures is essential for proactive corrosion management. Next, let us see case studies about soil corrosion. Numerous case studies illustrate the several consequences of unaddressed soil corrosion in infrastructure. One notable example is the failure of buried pipelines due to corrosion leading to environmental disasters. Learning from past events, one can help improve future designs and maintenance practices. Let us learn more about types of soil corrosion. Uniform corrosion occurs when the metal surface corrodes evenly. This is easier to predict and measure, though it can still lead to structural or weakening over time. Next is localized corrosion. There are three types in localized corrosion. They are pitting corrosion, device corrosion, and galvanic corrosion. Next is stake current corrosion. It is caused by external electrical currents such as those from nearby railway systems, electrical installations, or impressed current cathodic protection systems. These stake currents can accelerate metal loss in specific areas. Microbiological influence corrosion. This is caused by microorganisms, particularly bacteria like sulfate reducing bacteria. MIC can significantly accelerate the corrosion rate and often results in pitting. Next is numerous framework. There are various regulations governing the management of soil corrosion in different regions. Compliance with industry standards is essential for ensuring the safety and longevity of infrastructure. Awareness of local regulations can aid in developing effective corrosion management plans. Next is role of material selection. Selecting appropriate materials can significantly reduce the risk of corrosion in soil environments. Stainless steel and specialized alloys are often used in corrosive conditions due to their resistance. Knowledge of soil properties can guide engineers in making informed material choices. Monitoring technologies. Advanced monitoring technologies such as remote sensing and corrosion sensors are emerging in the field. These tools provide real time data on corrosion conditions, allowing for timely interventions. Integrating technology into corrosion management can enhance the longevity of infrastructure. Economic implications of soil corrosion. The economic impact of soil corrosion can be substantial, affecting maintenance and replacement cost. Infrastructure failures due to corrosion can result in significant downtime and associated losses. Investing in corrosion prevention and monitoring can lead to long term savings and safety. Next is future trends in social corrosion research. Research is ongoing to better understand the mechanisms and factorial influencing soil corrosion. Innovations in materials science may lead to the development of more corrosion resistant materials. Future studies may focus on the interaction between climate change and soil corrosivity. Educational initiatives. Raising awareness about soil corrosion is crucial for engineers, construction professionals, and the public. Educational programs can help inform stakeholders about best practices in corrosion management. Collaboration between industry and academia can foster research and innovation in the field. Next is role of engineers in corrosion management. Engineers play a critical role in designing and implementing effective corrosion control measures. Continuous education on the latest corrosion prevention techniques is a vital role for engineering professionals. Collaboration with multidisciplinary teams can enhance the effectiveness of corrosion management and strategies. Next we'll study about key soil properties impacting corrosion are redox potential, presence of organic material, cation exchange capacity, temperature and seasonal variation. The advanced mitigation techniques are electrochemical monitoring, anodic protection, inhibitors, geotextiles and protective liners, corrosion resist, backfill, etc. Soil corrosion testing and assessment are soil resistivity testing, pH and moisture testing, chemical analysis, corrosion coupons and proverbs. International perspectives of soil corrosion are soil corrosion is a global issue that affects infrastructure across different countries and climates. Sharing knowledge and best practices internationally can enhance global corrosion management efforts. International standards and guidelines can help harmonize approaches to soil corrosion. The conclusion of soil corrosion is soil corrosion is a complex phenomenon that requires comprehensive understanding and management. Proactive measures, including material selection, monitoring, and education, are essential for mitigation. Ongoing research and collaboration will be crucial for addressing future challenges in soil corrosion. Next is this, and then thank you.